It's review time. We're going to go through this review. I'm going to go a little bit quicker than normal just because I want to not have a 2-hour video because it is a long review. But if you have questions, obviously feel free to email or text through Remind, and we will get your answers so that you are ready. All right, here we go. Which of the following describes a situation where the normal condition is met, therefore T procedures can be utilized? So remember, for T procedures, that means we're looking at a mean problem. So that means we're going to need to check our samples. If the sample size is greater than 30, then I don't have to worry about any box plots. So the reason I mention that is because if you look right here on D, both of the sample size are greater than 30. So the fact that sample 2 has 2 outliers doesn't really matter. Okay, so sample 2 having 2 outliers does not matter because my sample size was bigger than 30 for both of those graphs. So this one is okay. A. So both of my samples are less than 30, and so it says here both samples are approximately normal with no outliers. Then that means that we can use our T procedures. In part B, or option B, it says that sample 1 is approximately normal, but sample 2, who only has a sample size of 5, is strongly skewed to the right. That is not okay. So that is a problem. In C, N being 30, that means that sample 2 is fine. There's nothing wrong with sample 2. We can go ahead and assume that sample 2 is good. But sample 1, we've got a sample of 15. And when we read the answer here, it says that both samples are moderately skewed. Moderate skew is fine. But sample 1 has an outlier. That is not okay. So C is off the table. So it looks like there's more than one of the situations that we could use our T procedures. All right, number 2. After once again losing a football game to their arch rival, the college's Alumni Association conducted a survey to see if the alumni were in favor of firing the coach. An SRS of 100 alumni from the population of all living alumni was taken, and 64 were in favor of firing the coach. Suppose you wish to see if a majority of living alumni are in favor of firing the coach. What is the appropriate test statistic? So we're looking at a proportion here, so obviously it's going to be a Z test statistic. And remember that to get our Z test statistic, we are going to do the value minus the mean of the distribution divided by the standard deviation or standard error. So for a test, a Z test, we're going to need the value of our sample. So this is going to be P hat. And we're going to subtract the mean of the sample distribution, which would be the claimed value. So it's going to be the claimed value from the actual population, or from the hypothesis, not the population, from the hypothesis. And then we're going to divide by the standard deviation of the hypothesized distribution. So that would be the square root of P naught 1 minus P naught divided by the sample size. So our hypotheses, right? So our null hypothesis would be that P equals 50%, meaning that there's not like a majority. It's just 50-50 want to fire the coach. The alternative is we're trying to see if a majority are in favor of firing the coach. So the proportion that want to fire the coach would have to be greater than 50%. So my P naught value, my hypothesized value, my claimed value is 50%. P hat is the sample proportion. And so that would be where the sample comes in of 64 over 100, which is 64% or 0.64. The hypothesized value is the 50%. And then my sample size was 100. These hypothesized values as well are 50%. So the one that matches this would be, 0.64, 0.5 on the bottom. This is a problem because this is using p hat on the bottom instead of our hypothesized value, and that is a problem. So that one's out. This one has these on the top switched, so that one's out. C says 0.64, that's the p hat. 0.5, that's our hypothesized value. 0.5 on the bottom, 0.5, and 100 is my sample size. So it looks like C is my answer. D, the issue here is, again, this bottom is wrong. And then E, the issue on E is that these two are switched. The bottom is right. The sample size is wrong, but that one is definitely out as well. Okay, so our answer there would be C. Number 3. Which of the following 95% confidence intervals would lead us to reject the null hypothesis that P equals 0.7 in favor of the alternative that P does not equal 0.7 at a 5% significance level? Just a reminder, if you're using a 95% confidence interval, then it should go with a significance level alpha of 0.05 or 5%. So which one would lead us to reject a null hypothesis that P is 0.7? So the only reason I would reject 0.7 is if it's not a possible value. So if I look at these, the first option has 0.7 in it, right? So 0.7 is a plausible value, so I wouldn't want to reject it. So that's not it. B also has 0.7 in it. C also has 0.7 in it, but D does not have 0.7 as a plausible value. And that's why I would reject it. Number 4. A researcher claims to have found a drug that causes people to grow taller. The coach of the basketball team at Brandon University has expressed interest but demands evidence. Over 1,000 Brandon student volunteers to participate in the experiment to test the new drug. 50 of the volunteers are randomly selected, their heights are measured, and they are given the drug. 2 weeks later, their heights are measured again. By the way, that would be a paired t-test. The power to detect an average increase in height of 1 inch could be increased by what? So power of the test, we're trying to increase the power of the test. There are 2 ways to increase power. If you want to increase power, then you need to do one of 2 things. Increase your sample size, N, or increase your alpha, your significance level. Okay, those are the 2 ways we can increase power. Increasing the sample size means that I have less of a chance of making an error because I have a lot of data from the population. So that gives me a lot of power in making sure that I am making the right decision. Increasing the sample size increases the probability of a type 1 error, but it increases the probability of a type 1 error, so therefore it increases the probability that I'm going to correctly reject the null hypothesis because it's going to be easier to get evidence if my alpha is high. Only volunteers for the basketball team are in the experiment. That doesn't change power. Using alpha of 0.01 instead of alpha of 0.05. That's actually decreasing alpha, so that would decrease power. Using an alpha of 0.05 instead of an alpha of 0.01. That would increase power. Giving the drug to 25 randomly selected students instead of 50. That would be decreasing power because that is decreasing the sample size. And then using a 2-sided test instead of a 1-sided test, that does nothing for power. That's just going to change my p-value, but it does nothing for power. Alrighty, number 5. Experiments on learning in animals sometimes measure how long it takes mice to make their way through a maze. The mean time is 18 seconds for one particular maze. A researcher thinks that a loud noise will cause the mice to complete the maze faster. She measures how long each of the 10 mice take with a loud noise as a stimulant. The appropriate hypotheses for the significance test are: we can immediately mark off C because we don't use a less than in a null hypothesis. We can immediately mark off E because we never use X bar in our null hypothesis. We think that a loud noise, or she's thinking and testing whether a loud noise makes them do the maze faster. So a faster completion would decrease the time it takes them. And so that would be a mean less than 18. So that would be D. Alrighty, number 6. Members of the City Council want to know if a majority of city residents support a 1% increase in the sales tax to fund road repairs. To investigate, they survey a random sample of 300 city residents and use the results to test the following hypotheses. The null hypothesis is that the true proportion is 50%. The alternative is that the true proportion is greater than 50%, a majority. P is the true proportion of all city residents who support a 1% increase in the sales tax to fund road repairs. Type 1 error in this context would mean what? So a type 1 is when we reject the null hypothesis because we have convincing evidence. So we reject the null hypothesis because we have convincing evidence, but the null hypothesis was true in reality. Okay, so in reality, the null hypothesis was actually true. So let's see. In a type 1 error, we have convincing evidence. So we find convincing evidence that a majority support the tax increase, when in reality, there isn't convincing evidence that the majority supports the increase. So in reality, there is not actually convincing evidence, even though I found convincing evidence, I should not, that really wasn't convincing evidence. Okay. In reality, there isn't really convincing evidence because I've made an error. So this sounds like the answer right here, but I'm going to go ahead and look at B, C, D, and E just to make sure. So I find convincing evidence that a majority support the tax increase, when in reality, at most 50% support the increase. So I can't really say that it is at most 50%, right? It could be that I've made some sort of, there's some sort of error in my sampling. I've got some sampling variability, some sample error. And so in reality, at most 50%, I don't know that it is at most. It might be less than that. It could be, I don't know. It's definitely just not, that's not what I'm actually finding here. I'm not finding at most 50%. I'm looking at trying to prove, what we're trying to prove here is that the true proportion is greater than 50%, and I haven't been able to prove that, okay? In reality, it could be equal to 50%. It could be something else, but I'm not sure. So that is the problem here, is this at most, okay? C, finds convincing evidence that the majority of residents support a tax increase, when reality more than, well, that's actually the alternative hypothesis, so that's not it. And then these last two, the issue is that it's not talking about a type 1 error correctly. If I've made a type 1 error, it's because I found convincing evidence. These are saying that I did not find convincing evidence, but actually do find convincing evidence in a type 1 error. I found convincing evidence when there really wasn't convincing evidence to be found. So it's kind of like I found a pretty bad sampling variability in my sample that I found. So that's kind of the issue there. That one's pretty confusing. Especially A and B. A and B both look really good. And I can kind of see I can kind of see an argument for either A or B, because it kind of sounds like they're both saying the same thing, but in reality, there isn't convincing evidence of a majority because we rejected, and we should not have done that, because we don't really have good evidence that the majority supports, and that's kind of the problem there. All right. So again, that one's kind of tricky. I don't think there's any that are going to be that trickily worded on your test. Okay, let's look at 7. On 7, it says, in the sample, 158 of the 300 residents support the 1% increase. What is the resulting p-value? So in this situation, we're just literally going to plug this into the calculator and get the p-value. So we're going to go to this one. When I read the problem, there was just one sample. So one sample. This was a proportion problem. I'm looking at a proportion that support the tax increase. Sorry, it's literally been a long day. One proportion. Since it's a proportion problem, it is going to be a z, and then I am testing to see if there is in fact a majority. So this is going to be a 1 prop z test. When you go to your calculator, that's going to be under stat test 5. Stat test 5, that's your 1 prop z test. The first thing it asks you is, what is your null hypothesis, or your claimed value? And so that is the 0.5 from the hypotheses. X, that's your number of successes in your sample. That's the 158. N is your sample size. That's the 300. And then what direction is your alternative hypothesis? The direction of the alternative hypothesis is that P is greater than the claimed value. And so that is going to be the one we should select. And then we get our Z test statistic, 0.924. That means that our sample was almost 1 standard deviation above, because it's positive, what the claim value is of 50%. The P value is 0.1778, and that corresponds to C. And what does that p-value actually mean? What that means is, if I assume that the claimed value is 50%, so giving the null hypothesis the benefit of the doubt, then our sample, which was the 158 out of 300, our sample was about 1 standard deviation above, this is a distance of 0.924. It was 1 standard deviation above average, and above the hypothesized value. And the probability of that being sampling variability is about 18%. And so we have a pretty good chance that this was just sampling variability. So again, assuming the null hypothesis is true, so assuming that 50% of residents support the tax increase, assuming that 50% of the residents support the tax increase, there is a 0.8 or 0.18 or 18% chance. So, sorry, I did not see that. Assuming that more than, that would be wrong. There is a 18% probability, an 18% chance, okay, that the sample proportion would be 0.527, that is what 158 over 300 is, or higher by chance alone, as extreme or more extreme by chance alone. The part E says there is an 18% chance that the null hypothesis is true. Nope, we do not have a probability of the null hypothesis being true. This is the probability that our sample is as extreme or more extreme than what we got, so it is 0.527 or higher just by chance or sampling variability. That is why C is the answer. All right, number 9. A sample survey interviews an SRS of 500 female college students and 550 male college students. Researchers want to determine whether there is a difference in the proportion of male and female college students who worked for pay last summer. In all, 410 of the females and 484 of the males say they worked for pay last summer. Take P sub M and P sub F to be the proportions of all college male and females who worked last summer. The hypotheses to be tested are what? So we're looking at, obviously, we can take those two out. We're looking at the difference in the proportion of males and females. We can take out D and E because they don't have the equal sign. So if you're looking at whether or not there is a difference, right? So we're trying to see, is there a difference? That would be that PM does not equal PF, and that just means PM minus PF is not equal to 0, which is A. Number 10, the researchers report that the results are statistically significant at the 1% level. What does it mean for something to be statistically significant? That means that our p-value was less than our alpha value, and we therefore rejected the null hypothesis. And why did we reject the null hypothesis? Because there is convincing evidence for the alternative hypothesis. So let's see which one we think it is. Because the p-value is less than alpha, the 1%, because the p-value is less than 1%. Okay, it looks like all those are going to be the same. Okay. We rejected the null hypothesis, so we can take those off. Reject the null, reject the null, reject the null. And when we rejected the null, there is convincing evidence, there is convincing evidence, there is convincing evidence, there is convincing evidence. Okay, now, there is convincing evidence of the alternative hypothesis, and that is the proportion of males does not equal the proportion for females. So there is convincing evidence that the proportion of all male college students who worked for pay last summer is the same at, nope, that's the null hypothesis. We got convincing evidence for the alternative hypothesis. There is convincing evidence that proportion of all male college students in the study, it's not that it's the ones in the study. We are doing all of these confidence intervals and hypothesis tests in order to see something about the true proportion, the true population. It's not about what's in the study. I don't have to do a test about what's in the study. I can just look at the data of the sample. So why would I write a hypothesis about the sample? That's what this is basically doing here. So the proportion of all male college students who worked for pay last summer is different than the proportion of all female college students who worked for pay last summer. That's the population, and that's why I'm doing this test. Okay, number 11. Which of the following is the correct test statistic for the difference in proportions of male and female college students who worked last summer? So again, our z-test statistic is going to be our value minus our mean divided by our standard deviation. Now, remember, our mean is our hypothesized mean. Our hypothesized mean. Our hypothesized mean is that P for male, the proportion of males equals the proportion for females. And therefore they have a difference of 0. So on a 2-sample test, whether it's means or proportions, your hypothesis is always that the difference is 0. So this mean right here ends up being 0 for a difference of means test. So our value is our value from our sample. So that's going to be p hat m minus p hat f. Okay, that's what our value is going to be. I'm going to subtract 0 from my hypothesized mean, which the mean difference would be 0. And then my standard deviation is going to be the supergiant square root of p hat m, 1 minus p hat m, divided by the sample size for the males, plus p hat f, 1 minus p hat f, divided by the sample size for the females. That kind of format is on your formula chart for a 2-sample, so you can look on the back side of your formula chart to find that. And so at this point now we just need to make sure we know which one is which. So p hat for the males, there was 484 out of the 550, and so that is going to be 0.88. The sample size for the males was 550. For the females, p hat for the females was 410 out of 500. And so that's 0.82. And the sample size for the females was 500. So I just need to find which one of these matches all of this. You'll notice on the top it does not say minus 0. You don't have to write minus 0 on the top. So we're looking for on the top here 0.88 for the males minus 0.82 for the females. So the first one is good, B is good, C is good, D has them backwards, E has them backwards. A here is just wrong because that is not a 2-sample, it's only doing 1 sample on the bottom, it's combining them on the bottom, and we don't do that. So we need to see which one of these is the correct one. They both are good on the sample sizes, but if you look really closely, on B, they are combining their proportions. So they're averaging their proportions for some reason. And that's just, why do you do that? Why would you do that? That's silly. So we're not going to do that. So C is our answer. Okay, let's look at 12. Oops, too far. Number 12. Popular wisdom is that eating pre-sweetened cereal tends to increase the number of dental cavities in children. A sample of children was, with parental consent, entered into a study and followed for several years. Each child was classified as a sweetened cereal lover or an unsweetened cereal lover. At the end of the study, the amount of tooth damage was measured. Here are the summary data. Assuming the necessary conditions for inference are met, which of the following is an appropriate 95% confidence interval for the difference in the mean tooth damage? We have 2 groups here, sweetened versus unsweetened, so that's 2. We are looking at the mean tooth damage. That means we're going to be doing a T procedure, and we are creating an interval here. And so the 2 mean T interval here, I would need to go to stat test 0. Stat test 0. It's going to ask you, do you have data or do you have stats? You have stats. You have the summary of all the stats right here in this chart. X bar 1 needs to be the mean of the sweetened group, so that would be 6.41. That's going to be your X bar 1. S sub X1 is the standard deviation of the sweetened group. And then N1 is the sample size of the sweetened group. Okay, so these are your X bars, these are your S sub X's, these are your sample sizes. X bar 2 is going to be 5.2. S sub X2 is going to be 15. Sample size for 2 is 15. Then it's going to ask you, what is your confidence level? That is 0.95. And then it's going to ask you for pooled, and you're going to go ahead and say no to pooled. And when you get your interval, you will find that the answer is B. Now, based on that confidence interval, which of the following conclusions would we make for the corresponding hypothesis test performed on the mean difference? So that would be that the mean for the sweetened equals the mean for the unsweetened. The alternative would be the mean for the sweetened does not equal the mean for the unsweetened. Now, because we used a 95% confidence level, that corresponds to an alpha value of 0.05. And we would basically be looking here for 0. Where is 0? Is 0 in the interval? So when you look at that interval from up above, negative 7.57 to 9.99, you notice that 0 is in this interval. So if 0 is in the interval, there's a possibility that there is no difference between this tooth decay. If 0 is a possible value, then that means that we would not want to reject it. So we should fail to reject the null hypothesis because 0 is in the interval. I don't want to reject a value that is possible. Okay? All right, number 14. A researcher wished to compare the average amount of time spent in extracurricular activities by high school students in a suburban school district and with that in a school district of a large city. The researchers obtained an SRS of 60 high school students in a large suburban school district and found that the mean time spent in extracurricular activities per week to be 6 hours, with a standard deviation of 3 hours. The researchers also obtained an independent SRS of 40 high school students in a large city school district and found the mean time spent in extracurricular activities per week to be 5 hours with a standard deviation of 2 hours. Suppose that the researcher decides to carry out a significance test to see if there is a difference between the suburban and the city districts. What hypothesis would you use to carry out the significance test? Basically, this is the state part of the 4-step process. So we will test at alpha equals. Now, it did not give us a significance level in our in our problem, and so since it did not give us a significance level, then we are going to go ahead and go with the baseline, which is 0.05. And our null hypothesis would be that the mean for the suburban is the same as the mean for the city. The alternative is that the mean for the suburban is different than the mean for the city. And then we would want to define our parameters. Mu sub s equals the true mean time spent in extracurricular in the large suburban school, and mu sub c equals the true mean difference time spent in extracurricular in the large city school. Okay, you don't have to rewrite all that. You can use those little quotation or ditto marks. All right, let's look at 15. This past fall, temperatures in a particular city seemed to fluctuate tremendously. The days often felt like summer and the nights often felt like winter. A weather analyst selected a simple random sample of 9 days from this past fall and recorded a high and low temperature in the city for each of these days. Now, each day they recorded a high and a low temperature, and we're looking at the difference in the high and the low. So each day is matched with itself, high and low. Which of the following satisfy the normal condition so that a T procedure can be used for paired data? This is paired data. So, in paired data, I do not care about the original two different values or those distributions. The only thing that is tested or has to meet conditions is the differences. So the distribution of high temperatures does not have to be normal. The distribution of low temperatures does not have to be normal. But the differences need to be normal, aka no strong skewness or outliers. I do not have to have both high-end temperatures, and it does not have to be all three. All right, so the answer would be C. And what are the hypotheses for the paired t-test from number 15 above? My bad. The paired t-test from number 15 above. Sorry about that. So this would be, we will test at alpha equals 0.05. Again, it didn't give us anything different, so we'll go ahead and use that. The null hypothesis. Now, this is going to be the most unrealistic situation ever. So basically here what we're saying is unrealistically that the mean difference is equal to 0, meaning the high and low temperature, that there's no difference in the high and low temperature. Like, obviously there is a difference in the high and low temperature. So this is just basically going to show how far the differences are, okay? The alternative is that the mean difference is different than 0. Technically, you probably could even do that the mean difference is greater than 0, showing that the high minus the low is a positive number. You could probably do that as well. Again, this is a very unrealistic statistical analysis, but you could probably do either one of those, and I'll tell you how that would work either way. So the mean difference, whenever we do the significance test, I'll show you how that would change your p-value. It's pretty easy. This would be your mean difference in high and low temperature. All right, and then we're going to go ahead and assume the conditions are met just because we don't need to do all those conditions. And we're going to calculate the t-test statistic and the p-value and make the appropriate conclusion at a 5% significance level. So what we're going to use here, we're going to use a paired t-test. Now, remember, that is very, very, very much just a one mean t-test. I'm just going to use the data from the table in order to do this, okay? So, this is going to be under stat test 2, the t-test. It just says t-test in your calculator. Stat test 2, it just says t-test in your calculator. Now, it's going to ask you, do you have data or do you have stats? Well, you do have the data. The data is in the table in number 15. You need to have your data in L1. All right, so your data needs to be in L1, your list. And then it's going to ask you, what is the mean, the hypothesized mean? We are hypothesizing very unrealistically that the mean difference in this high versus low temperature is 0. And so your mean mu sub naught is 0. Your list should be in L1. The frequency of that list is 1. And then if you guys will go ahead and select mu does not equal the claimed value of 0. And we'll talk about that one first, and then I'll tell you how that would change if you did this one. So first I'll show you if it's this, and then we'll talk about the other one. So if we select this one, then you're going to get a t-test statistic of 33.98. And that is giving you a p-value, this problem, that is giving you a p-value of 6.15 times 10 to the negative 10th. The chance that this was due to sampling variability is essentially 0. But basically, guys, what that means is that there is, we have super, super convincing evidence that the high and the low temperature are different. That's basically what we just proved. We have very great evidence that the high and low temperature are different. And the difference is 33.98, so 34 standard units from being the same. So that means that they do have really big swings in temperature in this particular city. If you had selected the greater than 0, okay? If you had selected, okay, I'm just going to do this. If you had selected that mu sub d was greater than 0, then you would still get a t-test statistic of 33.98 because that's how far away from them being equal to 0, but your p-value would be half, okay? So the p-value would only be half of this. So I believe it's like 3.07 times 10 to the negative 10th. So it's just it would be half of that p-value, because I would not be looking at, right, so we've got, this is our mean difference of 0, and we are 33.98 standard units from average, from having them be the same. In a two-sided test, your calculator also goes over here and finds that probability as well. In a one-sided test, it just doesn't do that side. Okay, so it just depends on which one you're doing. So either way, we have a super duper 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 small p-value, a ridiculously small p-value. And so now we're going to conclude. Let me scroll down here. And so for the conclude, our p-value, and either way, I'm just going to say it's essentially 0. And that is less than the alpha value of 0.05. So we're going to reject the null hypothesis. There is convincing, very convincing, there is convincing evidence that the true mean difference in the high and low temperature is not 0. We have very, very, very good evidence that the true mean difference is not 0. Obviously, our high and low did change, and it changed by a lot every time. So again, very silly, unrealistic example, but there it is. All right, so I'm going to go ahead and stop this video because this is already 43 minutes. And then I'm going to do another one that has number 18 till the end. So that's the end of this video, 1 through 17. Merry Christmas.